Hey guys, so today we are going to talk about section 2 of chapter 13, but before we get into that, we have to review special right triangles. Special right triangles are very, very important in this chapter. So in geometry, you learned about two special right triangles, the 45-45-90 triangle and the 30-60-90 triangle. The figures at the right summarize the relationships among the lengths of the sides of each triangle. So for this section, you need to memorize your special right triangle rules. First, we have a 45-45-90 triangle. A 45-45-90 triangle is an isosceles triangle, and the rules for this are your legs are congruent, so each we represent with S, and the hypotenuse is S radical 2. So for example, if you had a leg of length 1 unit, the hypotenuse would just be radical 2. For our 30-60-90 triangles, we have our side across from the 30-degree angle represented as S, across from the hypotenuse is 2S, and across from our 60-degree angle is S radical 3. So for example, in this one, if our shorter side, which is across from the 30-degree angle, is 1, our hypotenuse would be 2 times 1, which is just 2, and our longer side, which is across from the 60-degree angle, would just be radical 3. And remember, in all right triangles, your hypotenuse always has to be the longest side because it's across from the biggest angle. So in our 45-45-90 degree triangle, it's represented as radical 2. In our 30-60-90 triangle, in this case, is represented as 2. And before we get into section 2, let's do a problem of the day. So if you want to stop this video now and try it on your own, and then we can go over it, that's fine. So we're going to determine whether or not the function is periodic. Periodic functions follow a pattern. If it is, find the period, amplitude, and midline. So the easiest way to figure out your period is by looking at your maximums. But notice in this graph we have 2 points that hit our maximum and 2 points that hit our minimum. So between this maximum right here is not our full cycle. We're going to use this maximum here, which is the second peak of this M shape, and this maximum here, which is the second peak of the M shape again. So here we're at the x value of 0, here we're at the x value of 8, which means that our period, one full cycle, is going to be 8 units. So the period is 8. To figure out the amplitude, we need to know our maximum and our minimum values. In this case, the maximum is at 4, and the minimum is at -4. To find the amplitude, remember we do max minus min over 2. So our max is 4, minus -4 becomes +4 over 2. 8 over 2 gives us an amplitude of 4. So our amplitude is 4 and the period is 8. For the midline is directly in between our maximum and our minimum. So in this case of this graph, our midline is going to be at y equals 0. Remember, it's an equation of a line, so you have to have y equals 0. That represents your horizontal line. So moving on to section 2, angles and the unit circle. The objectives for this section are to work with angles in standard position and to find coordinates of the points on the unit circle. We have a few definitions to start. An angle in the coordinate plane is in standard position when the vertex is at the origin and one ray is on the positive x-axis. So positive x-axis we know is everything to the right of the origin. That's where all of your x values are positive. The ray on the x-axis is the initial side of the triangle. So the initial side of your triangle is always that on the positive x-axis. The other ray is the terminal side of the angle. So your angles obviously are made up by 2 rays. The initial side is always on the x-axis. The terminal side is just the other ray, wherever that may land. The measure of the angle in standard position is the amount of rotation from the initial side to the terminal side. So to figure out how many degrees this angle is, we start at the initial side and rotate around to the terminal side. Essential understanding for this section. The measure of an angle in standard position is the input for two important functions. The outputs are coordinates called cosine and sine of the point of the terminal side of the angle that is 1 unit from the origin. The measure of an angle is positive when the rotation from the initial side to the terminal side is counterclockwise direction. The measure is negative when the rotation is clockwise. And on the next slide, there'll be a diagram showing this. So from your initial side, which is always the x-axis, if you move in the counterclockwise direction, your angle is going to be positive. That's how we have positive 120. From our initial side on this diagram, if we move in the clockwise direction, your angle is going to be negative. That's how we have negative 120. So counterclockwise is always positive. Clockwise is always negative. We can use these rotations to figure out the measures of angles. So for A, we're looking at this angle that starts, our terminal side is always the x-axis, and rotates around to the y-axis. We're moving in a counterclockwise direction, so we know it has to be positive, so it's easy to tell in this case that we've moved positive 90 degrees. For B, it's a little bit trickier. We're moving from the initial side, we're moving in a clockwise direction, which means that our angle is going to be negative. First, from our initial side to the y-axis, that's a negative 90 degrees already. To figure out this other piece of the angle, we're going to create a right triangle. So we know, based off of this coordinate pair, that from the origin, we move 2 units down on the y-axis and 2 units left on the x-axis. And the reason I'm drawing this diagram here is because I'm trying to figure out how many degrees this angle is. So I've created my right triangle now. And if I'm moving negative 2 units down and negative 2 units to the left, that means that both of these sides of this triangle are congruent. If those two sides are congruent, it's going to be a 45, 45, 90 triangle. So we can assume that this angle, this leftover part here, is 45, but because we're moving in a clockwise direction, it's going to be negative 45 degrees. So to figure out the entire measure of this angle, we do negative 90 minus 45, to get negative 135 degrees. So that angle there is negative 135 degrees. You can tell the first part just by seeing it's 90 degrees, and then the next part you use your special right triangles. One more example. What is the measure of the angle shown? So now for this one, we're moving in the counterclockwise direction, so it has to be positive. From our initial side, we go a full 180 degrees. So we already have moved plus 180. So now we just have to figure out this remaining piece. So again, we're going to create a right triangle using the terminal side and the coordinate that we're given. So we have our terminal side to this point, and we're going to create this right triangle here. Again, like in the last problem, we moved the negative 2 units along the x-axis and negative 2 units on the y-axis. This creates an isosceles triangle, which means our other angles are both 45 degrees. So in this case, we have to do 180 plus 45, which is going to give us a total of positive 225 degrees. It's very important that you show your sign here so we know which direction we're going, either clockwise or counterclockwise. We can also sketch angles in standard position. So again, standard position, remember, means that your angle starts with the initial side on the positive x-axis. Because we're sketching, it's not going to be exact, so don't worry about using a protractor or anything. So for A, we have 36 degrees. Standard position means that our one side is always on the positive x-axis. 36 degrees is positive, so we're moving in a counterclockwise direction about a little more than a third of the way through this quadrant since it's 36 degrees. So the other side of this angle is approximately right there. For positive 315 degrees. Again, 315 means that we're moving in a counterclockwise direction. So from the x-axis, this is where our angle starts again. That's the initial side. We're going to go a full 180 degrees. Then we can go even further to get to 270 degrees when we get back to this y-axis down here. We need to get to 315 though, so we're going to go a little bit further here. And 315 is approximately this angle created there. Our third sketch for negative 150, again, you start with your initial side on the x-axis. Negative 150 means that we're moving in the clockwise direction. So from the initial side, we're going to go 90 degrees here. Now from here we have to go another 60 degrees, so almost at that 180, but not quite exactly. So that creates our angle of negative 150 degrees. Remember, for these, for standard position, you're always starting your angle on that positive x-axis. And let's look at one more example. So sketching angles in standard position. If you want to take a second and try on your own, you can pause the video now. Otherwise, we'll jump right in. So again, standard position, you have to start on the positive x-axis. So your initial side is always going to be there. For A, we have 85 degrees. Positive means that we're moving in the counterclockwise direction. 85 degrees is going to bring us very close to the y-axis, but not exactly there. So 85 degrees is going to be approximately right around there. For B, we have negative 320 degrees. So again, angle is starting on the positive x-axis. To get to negative 320 degrees, we're going to move in the clockwise direction. So we go 90 degrees, then we go 180, around to 270 degrees, then we have to go approximately 50 more degrees to complete this angle. So it's going to be right around halfway through this quadrant, and that's negative 320. Then for C, we have positive 180 degrees. So we start our angle on the positive x-axis. Because it's a positive angle, we're moving in the counterclockwise direction, and 180 is going to bring us straight across here, which just makes up the entire x-axis. Two angles in standard position are called coterminal angles if they have the same terminal side. So coterminal means they have the same terminal side. They share a terminal side. For example, angles in standard position that have measures of 135 degrees and negative 225 degrees are coterminal. So for 135 degrees, again, we always start our angle on the positive x-axis. We go 135 degrees in a counterclockwise direction. For our angle of negative 225, we go negative 225 degrees in the clockwise direction. Both of those angles bring us to the same exact terminal side, which makes them coterminal angles. To find coterminal angles, all we have to do is add or subtract 360 degrees. Because they both start in the same exact spot and end in the same exact spot, they make up a full 360 degrees. So given the angle of negative 60 degrees, determine a positive and negative coterminal angle. Before we determine our angles, we're first going to sketch negative 60 degrees. So start your initial side is always on the positive x-axis. Negative 60 degrees is 2/3 of the way. Because it's negative, we're going in a clockwise direction, so it's going to be right around there. So we start with our angle of negative 60 degrees. To find a positive coterminal angle, obviously if I want to make negative 60 positive, I have to add 360. So negative 60 degrees plus 360 is going to give me a coterminal angle of 300 degrees. To find a negative coterminal angle, obviously if I want this number to stay negative, I have to subtract 360. So negative 60 degrees minus 360 degrees is going to give us negative 420 degrees. So from my original angle, which is negative 60 degrees, I've created two coterminal angles. The first one is positive 300. So if I start at my initial side and move 300 degrees in a counterclockwise direction, I'll get back to this exact terminal side. And if I start with my initial side and then move negative 420 degrees, that's a full circle and then some. So I start here, I will get all the way back again to this terminal side. So last two examples for coterminal angles. Given the angles, determine the positive and negative coterminal angle. Take a second and solve both of these. So for A, we have an angle of negative 315 degrees. To find a positive coterminal angle, we do negative 315 degrees plus 360 degrees, which gives us positive 45 degrees. To find a negative coterminal angle, we do negative 315 minus 360 degrees, which equals negative 675 degrees. For B, to find our positive coterminal angle, and now I realize I probably should have switched the colors, but we'll go with it. To find our positive coterminal angle, we do 45 degrees plus 360 degrees, which gives us a positive coterminal angle of 405 degrees. And for the negative, we take 45 degrees minus 360 degrees, which gives us a negative coterminal angle of negative 315 degrees. A very important tool that we're going to be using when looking at angles in our coordinate plane is the unit circle. And this is what our unit circle looks like. Our unit circle always has a radius of 1 unit. So the unit circle hits every axis at 1. So on this case over here, on the x-axis, on the positive x-axis, our point is at 1, 0. On the positive y-axis, our point is 0, 1. Because we didn't move to the left or right at all, we just went up a unit. On the negative x-axis, our point is at negative 1, 0, and on the negative y-axis, our point is at 0, negative 1. This is always true for the unit circle. And with using the unit circle, we're able to create different triangles to find the measures of angles. And in our unit circle, it's also very important to remember that the radius is 1 unit, but also the hypotenuse of any right triangle that you create is also 1 unit, because still for the hypotenuse of a triangle with a point on the unit circle, you're just going from the center to the edge of the unit circle, which is still your radius. You can use the symbol theta for the measure of an angle in standard position. And remember, standard position, don't forget, is when you have the initial side of your angle on the positive x-axis. So a little summary for the unit circle. In a 360 degree angle, a 0.1 unit from the origin on the terminal ray makes 1 full rotation about the origin. The resulting circle is a unit circle. So really all that's saying is we have our axis and we have a circle that hits, well, that's a little off, but it hits positive 1 on the x-axis, positive 1 on the y-axis, negative 1 on the x-axis, and negative 1 on the y-axis, not to scale. The unit circle has a radius of 1 unit and its center at the origin of the coordinate plane. Any right triangle formed by the radius of the unit circle has a hypotenuse of positive 1. Points on the unit circle are related to periodic functions. Key concept for cosine and sine of an angle. Suppose an angle in standard position has a measure theta. The cosine of theta is the x-coordinate of the point at which the terminal side of the angle intersects the unit circle. The sine of theta is the y coordinate. So if you're trying to find the cosine or the sine of an angle, you can use the terminal side, which is the side that's the opposite the initial side, not on your positive x-axis. Wherever that terminal side intersects your unit circle, whatever point that is, your x value of that point is going to represent cosine of that angle. The y value of that point is going to represent the sine of your angle. So finding cosines and sines of angles. What are cosine theta and sine theta for? So first we have 90 degrees. Theta equals 90 degrees. Again, it's very important to remember for your unit circle, we hit our x and our y axis at 4 points. So to find the cosine and sine of 90 degrees, we're going to start with our initial side on the positive x-axis. For 90 degrees, we rotate counterclockwise, and our angle, our terminal side of our angle, is going to be on the y-axis. We know that this point on our terminal side is going to be at 0, 1. So for the cosine of 90 degrees, cosine of 90 degrees is represented by the x value, so cosine of 90 degrees is going to be 0. For sine of 90 degrees, sine is represented by our y value, so sine of 90 degrees is going to be 1. For theta of negative 180, we start our angle on this initial side on the positive x-axis, negative 180, so we're moving clockwise 180 degrees until we have this straight line across. This point on our terminal side for negative 180 is at negative 1, 0, which means that cosine of negative 180 is going to be our x value, so it's negative 1, and the sine of negative 180 is going to be the y value, which is 0. And finally, for theta of 270. So we start our initial side on the positive x-axis. Positive 270 degrees means that we're moving in the counterclockwise direction. We go 180 degrees and then 90 more degrees to get to 270. So this is our angle that's going to be formed. It's on the negative y-axis where our point is 0, negative 1. So cosine of 270 is going to be 0, which is represented by the x value, and sine of 270 is going to be negative 1, which is represented by the y value. Another example, what are cosine theta and sine theta for negative 90 degrees, negative 360 degrees, and 540 degrees. So for negative 90 degrees, we start our angle as always on the initial side. Negative 90 degrees means that we're moving in a clockwise direction. So we're going to be on the negative y-axis. So cosine of negative 90 is represented by the x value of this point, and this point is at 0, negative 1. So cosine of negative 90 is going to be 0, and the sine of negative 90 is going to be negative 1. For negative 360, we start our angle on the initial side. Negative means that we're moving in a clockwise direction, so we're going to go 360 degrees, and we land right back on the positive x-axis. Our point here is 1, 0, which means that the cosine of negative 360 degrees is positive 1, our x value, and the sine of negative 360 degrees is 0, which is our y value. And finally, when theta is 540 degrees. So 540 degrees, we start our initial side, and we're moving in a counterclockwise direction since our angle is negative. To get to 540, we have to go a full 360 degrees, so we're back at our initial side, and then an extra 180 degrees to get to 540. So our point is going to be on the negative x-axis. This point here is at negative 1, 0. So our cosine for 540 degrees is our x value, so -1, and the sine of 540 degrees is going to be the y value, which is 0. We can also figure out our coterminal angle to 540 degrees, another positive coterminal angle, by subtracting 540 minus 360 degrees, which is 180 degrees. And because these angles are coterminal, we know that the sine and the cosine of 540 degrees is going to be the same as the sine and the cosine of 180 degrees, because your terminal side is what's determining which coordinates you're using on your unit circle for the sine and the cosine. So it's pretty easy if you're given a angle where the terminal side is on an axis, it's pretty easy to figure out the cosine and the sine because you're just trying to figure out the point where it hits. But we can also use our unit circle to find the exact values of sine and cosine for angles that are multiples of 30 degrees or 45 degrees. So let's look at an example with 45 degrees. So here's our unit circle with one triangle where we have 45 degree and a 45 degree angle here. The rules for these special right triangles are just off to the side here. You need to memorize these. These are very important. So we have 4 angles on our triangle that split these quadrants in half. So each quadrant is 90 degrees. So your 45 degree angle is going to split each of these in half. We can use the rules of our special right triangles to figure out these points on the unit circle, because now it's a little bit trickier that we're not actually on an axis. So we can create a right triangle here. We have a 45, 45, 90 triangle. Remember, for unit circles, we know that our hypotenuse is always 1 because it is the radius of our unit circle. So using that, we can figure out our x and our y values of this coordinate using the legs of our triangle. So with the rules of a 45, 45, 90 triangle, our hypotenuse is represented as s radical 2, and our legs are represented as s. So if our hypotenuse in this case is 1, our y value is going to be 1 over radical 2. But remember, when we're doing these, we never want to have a radical in our denominator, so we have to rationalize. 1 over radical 2, we can rationalize by multiplying the numerator and the denominator by radical 2. When we do this, we get radical 2 over 2. So the legs of this triangle, both of the legs, remember, they're always congruent because it's a 45, 45, 90 triangle. Both of the legs are going to be radical 2 over 2. So the point, this point on our unit circle is at radical 2 over 2, radical 2 over 2. So that represents the sine and the cosine of our 45 degree angle. We can use the same logic to figure out this point over here. With this 45 degree angle, we're going to make a right triangle. Our hypotenuse again is always 1, so we know our legs are going to be radical 2 over 2. But in this case, it's a little bit different because notice, remember, we're going from our origin. So when we're moving along the x-axis now, we're moving in to the negative part of our x-axis. So our x value here has to be negative. So our x value is going to be negative radical 2 over 2. For our y value, we're still moving up. So x is negative, but y is positive, so y is going to be radical 2 over 2. For our 45 degree angle here, we can create this right triangle. We know the sides are going to have to be radical 2 over 2. It just might, the sign might depend on where we are, which quadrant we're in. So as we're moving on the x-axis, we're moving in negative direction, so it's going to be negative radical 2 over 2. For our y value, we're moving down, so it's also going to be negative radical 2 over 2. And finally, for this 45 degree angle here, I'm going to get rid of this side so we can see. Create this right triangle. Our x, now we're moving in the positive direction on our x-axis. So our x value is going to be radical 2 over 2. For y, we're moving down, so it's going to be negative radical 2 over 2. These rules are always hold true in your unit circle. So using this special right triangle, we're able to figure out the sine and the cosine of a 45-degree angle, of a 135-degree angle, of a 225-degree angle, and of a 315-degree angle. And these values, these x and y values, are never going to change because the hypotenuse of these triangles is always 1 because it's contained in the unit circle. We can use similar rules with a 30, 60, 90 triangle. So our rules over here for 30, 60, 90, it's a little bit different because our two sides are not congruent. So if we have a 30, 60, 90 triangle where the hypotenuse is 1, our shorter side is going to be 1 over 2. And our longer side, which is opposite the 60-degree angle, is going to be radical 3 over 2. Which makes our x value, or the cosine of this angle, is radical 3 over 2, and the sine, or the y value, is 1/2. And just like our 45, 45, 90 triangle, these numbers for the most part are going to stay the same. They might flip depending on if it's a 30-degree theta or a 60-degree theta, and they might become positive or negative depending on which quadrant you're in. So if we look at this 60-degree triangle here, 30, 60, 90, which 60 degree is our theta. Now it's a little bit different. Across from the 30-degree angle is going to be negative 1/2 because we're moving on to the negative part of our x-axis, and across from the 60-degree angle is negative radical 3 over 2. So the coordinate pair here is going to be negative 1/2, negative radical 3 over 2. So again, we can use these rules to figure out the sine and the cosine of any angles that are a multiple of 30 degrees. So this is a look at our entire unit circle. Based off of the two triangles that we just went over, we can find out the sine and the cosine of any of these angles because they're all either multiples of 45 or multiples of 30. So let's look at a few examples. First, what are the cosine and sine of the angle? So we have theta equals 60 degrees. So if our theta is 60 degrees, remember our hypotenuse is always 1, which makes the side opposite the 60-degree angle radical 3 over 2, and the side opposite our 30-degree angle 1/2. So the point on our unit circle is going to be positive 1/2, positive radical 3 over 2. And remember, for these, our cosine of theta is always represented by the x-coordinate, and our sine of theta is always represented by the y-coordinate. So cosine of 60 is 1/2, and the sine of 60 degrees is radical 3 over 2. And for our next example, what are the sine and cosine of the angle? Theta equals 225 degrees. So 225, we're starting our initial side on the positive x-axis, and because it's positive, we're moving in the counterclockwise direction. So we're going a full 180 degrees, and then 225 is going to give us 45 degrees extra here. So we're going to be approximately right around here on our unit circle. This forms a 45-degree angle. So we have a 45, 45, 90 right triangle. So for our legs, our x is going to be negative radical 2 over 2 because we're in the negative values on the x-axis, and our y is also going to be negative radical 2 over 2 because we're in the negative for the y-axis. So our point here, negative radical 2 over 2, negative radical 2 over 2. Again, the cosine of theta is represented by the x-coordinate, and the sine is represented by the y-coordinate. So the cosine of 225 degrees is going to be negative radical 2 over 2, and the sine of 225 degrees is going to be negative radical 2 over 2 as well. Last example. If we can get to it, there we go. Last example, what are the sine and cosine of the angle? So first we have theta of negative 45 degrees. So negative 45 degrees from our initial angle is going to be directly cut in half, our fourth quadrant. So we have our right triangle here, 45, 45, 90 triangle. Our legs, x is going to be positive because we're on the positive x-axis, so it's going to be radical 2 over 2, and y is going to be negative, so negative radical 2 over 2. So this point on our terminal side is going to be radical 2 over 2, negative radical 2 over 2, which tells us that the cosine of negative 45, represented by the x value, is radical 2 over 2, and the sine of negative 45, represented by the y value, is negative radical 2 over 2. And for b, we have theta of 150. So from our initial side, it's positive, so we're moving in the counterclockwise direction all the way over here, and our angle is going to be here. This angle is going to form a 30, 60, 90 triangle. So our point here is going to be negative radical 3 over 2, comma, positive 1/2. X is negative because we're on the negative part of the x-axis, and y is positive because we're on the positive y-axis. So cosine of 150 is going to be negative radical 3 over 2, and sine of 150 is going to be positive 1/2. Your homework for this section is posted to Google Classroom. If you have any questions, please don't hesitate to reach out. Good luck.